Hello and welcome to yet another video of Cornerstones of Math. In my last video, I have solved these two equations with floor functions. However, those two equations were fairly easy, so today I am going to solve another equation which is more challenging compared to those in my last video. So now the equation is x squared minus 2 times floor x minus 8 equals 0. Here I am going to show you two methods. The first method is what I consider to be more general method that can be applied to many different forms of equations. The second method is less general, and it heavily relies on what I would call guessing the roots or trial and error. But hey, it can be quicker and less advanced compared to the first method, so I think it's worth mentioning. In the first method, we start by introducing a fancy way to express the real number x using floor function. We can express x as floor of x plus alpha, where alpha is greater than or equal to 0 and less than 1. Since floor x is an integer part of x, we can think of alpha as a fractional part of x. Moreover, throughout this method, let us write floor x as just n, just for the sake of simplicity, because this floor x is actually quite annoying to write with a pen and a pad, while n is considerably quick and easy to write. So we have x equals integer part n plus fractional part alpha. N is integer, and alpha is greater than or equal to 0 and less than 1. Therefore, we can write the given equation as n plus alpha squared minus 2n minus 8 equals 0. The gist of the first method is that we solve for alpha because we have the useful range condition for alpha. So let us solve for alpha. Here we have alpha inside the completed square, so instead of expanding, let us write n plus alpha squared equals 2n plus 8. Hence n plus alpha equals plus minus square root of 2n plus 8. So we have alpha equals minus n plus minus square root of 2n plus 8. So we have two possible expressions for alpha, one with plus sign and the other with minus sign. Let's examine each case. First, when alpha equals minus n plus square root of 2n plus 8. Now it's time to use the range condition that alpha is greater than or equal to 0 and less than 1. So we have minus n plus square root of 2n plus 8 is greater than or equal to 0 and less than 1. Here we have two inequalities, so let's tackle them one by one. First, minus n plus square root of 2n plus 8 is greater than or equal to 0. This is the radical inequality, and the graphical method can be very efficient for this kind of inequalities. First, let us write n is less than or equal to square root of 2n plus 8. And let us think about the graphs of y equals n and y equals square root of 2n plus 8. We need to find the intersection point in order to solve the inequality. The coordinates of the intersection point can be found from the equation n equals square root of 2n plus 8. And if we square both sides, we have n squared equals 2n plus 8. So n squared minus 2n minus 8 equals 0. So n plus 2, n minus 4 equals 0. So we have n equals negative 2 and 4. Here, notice that n equals negative 2 is the intersection point between y equals n and y equals minus square root of 2n plus 8. This wrong root is obtained because we can arrive at the same part by squaring both sides of n equals minus square root of 2n plus 8. The actual intersection point between y equals n and y equals square root of 2n plus 8 occurs at n equals 4. In order to solve the inequality, we use the graphs to find the range where the line is located below the radical function. And we also use the fact that the radical function is defined only on n greater than or equal to negative 4. So the solution is n is greater than or equal to negative 4 and less than or equal to 4. If we impose the integer condition for n, possible values are negative 4, negative 3, negative 2, and so on, all the way up to 4. Next, the other inequality, minus n plus square root of 2n plus 8 is less than 1. We used a similar graphical approach. So we have square root of 2n plus 8 is less than n plus 1. So let us draw the graphs of y equals square root of 2n plus 8 and y equals n plus 1 and find the intersection points. From the equation square root of 2n plus 8 equals n plus 1, if we square both sides, we obtain 2n plus 8 equals n squared plus 2n plus 1, which gives n squared equals 7, hence n equals plus minus square root of 7. Notice that n equals negative square root of 7 is the intersection point between y equals n plus 1 and y equals minus square root of 2n plus 8, and n equals square root of 7 is the intersection point between y equals n plus 1 and y equals positive square root of 2n plus 8. From the graphs, we now search for the range where the line is above the radical function, which is n is greater than square root of 7. The integer values that satisfy this range are n equals 3, 4, and so on. Therefore, by finding the common range between these two, we have integer solutions 3 and 4. This is obtained under the case where alpha equals minus n plus square root of 2n plus 8. So when n equals 3, we have alpha equals minus 3 plus square root of 14. Hence x, which equals n plus alpha, is equal to square root of 14. When n equals 4, and alpha equals minus 4 plus square root of 16, which is 0. Hence, x is just 4. These values are obtained by assuming plus sign here in the alpha. But we have the other case. When alpha equals minus n minus square root of 2n plus 8. The procedure is essentially the same, so I will speed up a little bit. Since alpha is greater than or equal to 0 and less than 1, we now have the inequality minus n minus square root of 2n plus 8 is greater than or equal to 0 and less than 1. From the inequality on the left, we have n is less than or equal to minus square root of 2n plus 8. Here, the graphs are essentially the same as the previous case, except this time, we use the graph of y equals minus square root of 2n plus 8 for the radical function. We still have the same coordinates for the intersection point, negative 2 here and 4 here. This time, we have to find the range where the line is below the lower radical function. We also have to take into account that the radical function is defined only on x greater than or equal to negative 4. Therefore, possible range for n is greater than or equal to negative 4 and less than or equal to negative 2. Hence, the integer values are negative 4, negative 3, and negative 2. The inequality on the right is also dealt similarly, using minus square root of 2n plus 8 is less than n plus 1. So we use this second graph, which we have already drawn before, with intersection points at n equals negative square root of 7 and n equals square root of 7. So this time the linear graph must be located above the lower radical graph, so we obtain n is greater than negative square root of 7. So the integer values are negative 2, negative 1, 0, and so on. So if we look for the common range between these two, we now have n equals negative 2 as the only common value. This gives alpha equals 2 minus square root of 4, which is 0 again. So x is n plus alpha, so it is negative 2. Therefore, from cases 1 and 2, if we write all possible values for x in an increasing order, we have negative 2, square root of 14, and 4. Next, the second method. This method also involves graphs, but different graphs from the first and relies a bit more on the intuition. We can write the equation as x squared equals 2 times floor x plus 8. Therefore, we now use the graphs of y equals x squared and y equals 2x plus 8. The graph of the actual right-hand side, y equals 2 floor x plus 8, is just below the graph of y equals 2x plus 8, so the overall trend that I'm going to explain applies to both green and orange graphs. Two graphs meet at x equals negative 2 and x equals 4. In the outer parts, the quadratic function has larger values, and the gap between two graphs becomes larger and larger as the magnitude of x gets larger and larger. This is something that we intuitively understand without applying advanced limits or calculus. Therefore, we only need to check this narrow range in the middle. In fact, we only need to check the small vicinity of the intersection points negative 2 and 4, because we know that in the middle, now the parabola is way below the linear function to make any contact. So the procedure looks like this. We have these integer values for this floor x on the right-hand side of the equation. Then, using these values, we calculate 2 times floor x plus 8 on the right-hand side. This has to equal x squared if it is indeed a root. So the value of x comes from the positive or negative square roots of these values. Then we can find the values of floor x using these obtained x values in the third row. And if x actually satisfies the given equation, then the value of floor x obtained from the square roots of the right-hand side must be equal to the value of floor x we have initially assigned and used to calculate the right-hand side. And if you look at the table, you can spot the match at this negative 2 right here, corresponding to the x value of negative 2. Also, we have 4 here and 4 here, which gives x value of 4. Additionally, if we use 3 for floor x, then the square root of the right-hand side also gives 3. In this case, x has the value of positive square root of 14. These are the only possible cases. Therefore, the roots are x equals negative 2 square root of 14 and 4. And that's all for today's video. Thank you for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.